Hello everyone, welcome back. This is the fourth video in OSPF learning series, and today we are going to go through different states in OSPF adjacency process. When two routers form OSPF neighborship, they transition over different states before establishing full adjacency with each other. The states are down, init, two-way, XART, exchange, loading, and full. As you see here in the diagram, I have two routers R1 and R2 connected back to back. I will be explaining each state with packet captures and logs taken from R1. The first state is down. An OSPF router starts with the down state, which means the router haven't received any hello message from its neighbors. But the routers can send a hello to its neighbor. As you see here in this diagram, both R1 and R2 starts off in down state. Then R1 sends a hello to R2. When R2 received this hello, R2 transitioned to init state. The thing to note here is, in the received hello message, R2's IP address is not mentioned in the neighbor field. Here in this case, it is obvious. Both routers doesn't know each other. They are just booting up, or OSPF is enabled for the first time. So R1 doesn't know R2 exists. So R1's hello message doesn't have R2's IP address. But now R2 knows that R1 exists because it just received a hello from R1. So when R2 sends a hello back to R1, R1's IP address will be present inside the neighbor field. Once R1 receives this hello from R2 and the hello had R1's IP address in the neighbor field, it doesn't go to init state. Instead, it will move to two-way state. So let's go over a packet capture to see what I have just explained. So here I have a packet capture which was taken in R1. I'll just filter with OSPF. So here if you see, the first hello is from R1 to the multicast address. And if you open the hello packet, we will not see neighbor field. That explains what I have mentioned in the slide. The first hello message, neighbor field will be empty. R2's IP address is not present. Whereas the reply from R2 to R1, you can see that there is a neighbor field and the neighbor field is updated with the R1's IP address. Once both routers exchanges their hello message and if they see each other, which means if R1 gets a hello message with R1's IP address in the neighbor field, then the router will move to two-way state. Once both routers reaches two-way state, then we can say that these routers are OSPF neighbors, which means they see each other but not yet started routing information exchange. Also, if this is a broadcast multi-access network, then DR-BDR election will start in two-way state. I have explained how DR-BDR election works in a different video, which I will link it here. The next state is XStart, and this is where the master-slave election will take place. The master router will control the routing information exchange. So this is how the XART state looks like. Initially, an empty DBD will be exchanged between both the routers, and this empty DBD will have the router ID, priority, MTU, etc. Based on the highest router ID, a router will be elected as the master, and the other router will become slave. Here, R1 sends an empty DBD first, and then it receives an empty DBD from R2. When R1 gets the DBD, since R2 is having highest IP address, R2 becomes the master and R1 becomes the slave. If we look at the packet capture, we can see that R1 is sending an empty DBD to R2 and R2 is sending an empty DBD back to R1. So let's just look at the DBD. So inside the DBD, we can see that there is MTU, there is sequence number, and there are some of the flags which I mentioned in the DBD video. So here if you see, the first one is I bit. I bit is set to notify the neighbor that this is the first DBD. The next one is more bit. So more bit is set when we have more DBDs to send. So if this was the last DBD, then more bit will be 0. The next one is master slave bit. So before the master slave election, both routers will set this bit as master, which means both of them are saying I am the master. But after master slave election, only master's DBD will have MS bit set. We can see that MS bit was set in both R1's and R2's empty DBD. The next state is exchange state, and the actual routing information exchange happens in this state. In the previous state, both master-slave election was completed and R2 was elected as the master. Master has to initiate the LSA exchange, and the slave is only allowed to respond back to the master's DBD. And the slave must respond to master's DBD even if there is no LSAs present. So in R1's perspective, when it received an empty DBD initially in the XART phase, R1 elected R2 as the master. So R1 already got master's DBD. Now it's R1's turn to respond back to master's DBD. So R1 will send all its LSA headers in a new DBD with master's empty DBD sequence number. So if you look at the packet capture, this was the empty DBD sent from R2 to R1 and the sequence number was 2191. So when R1 responds back to R2, it will use the same sequence number, and inside this DBD we can see that there are LSA headers present. Now R2 got all LSA headers from R1, but R2 had only shared an empty DBD previously. But R2 have few LSAs in its LSDB. So now R2 will send a new DBD with its LSA headers, and the sequence number of this DBD will be incremented by 1. Only the master can increment the sequence number. If you look at the packet capture, here you can see that R2 is sending a DBD back to R1. The sequence number got incremented by 1 and it has the LSA headers which is present inside R2. Now the slave router R1 receives this DBD from master and it is supposed to respond back with the master sequence number. Since R1 doesn't have any more LSAs to share, R1 will share an empty DBD copying master sequence number. We can see that here the sequence number is 2192, which was master's previous sequence number, and it's an empty DBD because here is no LSAs. And since it doesn't have any more LSAs to share, the more bit will also be set as 0. If this more bit was set as 1 and if we shared more LSAs to master, the master router R2 knows that the slave router R1 have even more LSAs to share. But master router R2 doesn't have any more LSAs to share. In that case, master will send an empty DBD to slave till slave sets more bit to 0. The next state is called loading. After exchange state, each router knows each other's LSA headers exchanged via DBDs. But the router needs to know more details about all the LSAs. So each router will exchange LSA info using link state request and link state update messages. First, R1 is sending a link state request to R2. In the packet capture, we can see that R1 is sending a link state request to R2, and inside that it is asking for the router LSA of router 2. Once R2 receives this link state request, R2 will respond back with a link state update message. So inside the link state update message, we can see that router LSA of R2 is shared to R1. Here all the details of that router's router LSA is present. Also R2 is sending its own link state request to R1, and if we look at that link state request, we can see that R2 is asking R1's router LSA. Then R1 will respond back with link state update, and if we look at the packet capture, we can see that R1's router LSA will be shared in that particular link state update message. If there is a link state request, then the response LSUs are unique as to whoever asked for that update. But then the router will share the same LSUs to the OSPF multicast group. We can see that here R1 and R2 is sharing the LS update to the multicast OSPF group. Also, one more thing is that all the LSAs has to be acknowledged back by the routers. As you see here in the packet capture, we can see that R1 and R2 is sending link state acknowledgements. The link state acknowledgement will have the LSA headers of the LSAs which it is acknowledging. This acknowledgement is to make sure that LSAs are not lost in transit, and if they are missed, it can be retransmitted, similar to how acknowledgement works in TCP. Once the loading process is complete, the neighbors will move to full state, which means that neighborship process is complete. To reiterate, when the routers see each other, it will reach two-way state and we call them as neighbors. And once they exchange their routing information and reaches full state, then we say that they reached full adjacency. Hope you liked the video and please share your feedback in the comments so that I can improve the future videos. Thanks for watching.